So what do? I work in distributed quantum computing. Distributed quantum computing is basically the setting where you have multiple network quantum devices that are interconnected via quantum networks, and their goal is to complete a quantum computation that is larger than what they could individually do themselves. So none of these devices can actually complete this computation without the help of others. And they can be kind of in the same room or in places very, very far apart, but they must be fully independent, meaning like they have to have their own hardware, their own middleware. It's not, multiple chips within one device. And what we're going to do, or what I do, is basically I study how to partition computations, partition things like quantum circuits, in order to distribute them. So a quantum computation has different parts. The first part in a quantum circuit would be its initialization, meaning just saying how many qubits you're going to use and in what state you're going to start. In this case, we start in the zero-ket state. Then we move into the actual computations that you can do with these states. So it can be one-qubit gates, where you're just kind of rotating your state in the block sphere, or they can be multi-qubit gates, where you're basically entangling multiple states in a way in which, if one is in a specific position, there's a consequence to another. And finally, you can measure them and bring them back down to bits. The idea for me, or in the context of distribution, is that you want to cut up these computations such that you send different parts of them to different devices. You can do this very clearly with qubits, with these wires that represent like the path that a qubit goes through when it's going through a computation, because you can basically just teleport a state from one QPU to the other, just send it off and say, well, it moved from this device to this other device. You can also do that with multi-qubit gates, such as these CNOTs, by using something we call communication primitives, which in essence are just these kind of operations that allow us to make multi-qubit operations non-local by either teleporting states at the start or using cat entanglers and disentanglers, which are basically these constructions that enable us to have, 2 qubits positioned in different devices that are now entangled via this operation. This kind of allows us to do what I said before, which is have one device have certain parts of the computation and another have others. Now, that looks very nice, but if I give you something like this and I tell you, now partition this up in a way in which we minimize the amount of communication that we need to do between two devices, which at the end of the day is the most expensive thing in our setting, you wouldn't necessarily be able to do it. It's a very, very large computation, and it just looks awful, right? And that's kind of the thing that we work with in distributed quantum computing. We have to have these super large computations because we're working in the regime where a device cannot do it itself. And devices now are like in the 100 to 1,000 qubit range in terms of what they can do. So we're talking about computations that are more than 1,000 qubits that need to be assigned to 2 or many devices that look absolutely awful. And whereas what do we do? Like, how do we minimize the cost of assigning these computations and cutting them up? Well, what we do is we firstly abstract these computations into hypergraphs. A hypergraph, it's kind of like a graph, but instead of having edges connecting multiple nodes, it has hyperedges connecting vertices. And these hyperedges are basically just showcasing the correlations that exist between many of these quantum states. They are directed because your computations are directed, so you just respect the same direction. And you can think of them as groupings of these nodes that in essence represent qubits and the transformations and the computations that may be done in these qubits, And then you also have something like a network graph, which is basically, well, what quantum devices do you have and what capacity do they have? We're talking, as I said before, about things that have more than 2, 3, and 1 qubit capacities, but it's just much simpler for us to talk about it in that range in order for us, to visualize it. And our goal is to, having this hypergraph that is representing a quantum computation and having this graph that is representing our network, how do we assign different parts of a computation to different devices? A possible solution in this setting would be something like this. And our goal is always to, firstly and most importantly, to respect our qubit capacities. So we can't assign, 4 qubits to the device, can only have 3 qubits. But also, in a second, but also very important scale, is to minimize the amount of communication, aka the amount of these like groupings that we're cutting through. when we do our mapping. This is an NP-hard problem. It's quite complicated, and it will require probably many years of joint effort by everybody to kind of solve in a way that is done quickly, within these large-scale networks, and also cheaply in terms of the computation that is required to solve the problem. But it's not only a communication question, right? So if you think about distributed computing outside of the quantum sense, if you go back to the classical world, one of the main things or the main reasons for us to distribute computations is to minimize the actual amount of time that a computation would take. So to parallelize, to have, different threads working together. And that is also another aspect or another angle that we could look at this problem from. Then there's the problem of noise. In quantum settings, you have a lot of noise within your devices, and it kind of destroys the entire computation. And when you have, devices collaborating and having to send things over networks, that's even worse, because quantum networks have even higher noises, different types of noises that are injected every single time you do a non-local computation. Then you've got things like, you could have two CNOTs, so two qubit gates together, and be able to send them over only one EPR pair, over only one communication, one entanglement. And this, this idea of burst communication, this idea of being able to optimize the amount of communication that we have, is also like a different aspect of it. Maybe, the groupings that we originally have in our hyperedge aren't necessarily exactly what we're going to need to send over. We can optimize, we can minimize that even further. We can also, we should start exploring how, we could exploit recurring structural patterns that arise in these hypergraphs in order to build, specific partitioners that solve this problem, rather than the hypergraph partitioning problem, which is kind of a simpler version of this that has been previously explored in the literature outside of the DQC context. And just kind of exploring the question of what type of partitioners would be better, whereas we should be looking at things that are, greedily partitioning or more advanced multi-level partitioners, is an interesting avenue for us in the field. Now, beyond partitioning, there's a lot of other big open questions in distributed quantum computing in the field that are still relatively unexplored. One of them is the offload in hybrid systems. So if you have a system where you have, multiple network devices and some of them are quantum, some of them are classical, how do you, decide what gets sent where? How do you decide a part of a computation is, simple enough to offload in a simulation setting, for instance, to a classical device if you're a quantum player, or the other way around. If you're a classical player, if you've got a classical device, how do you decide when you send things to a quantum computer? Then there's a question of distributed error correction and how we create and map codes in distributed settings. There's, as I've said a little bit before, this question of optimizing for distribution, and not only in the context of, doing burst communication and basically sending multiple entangling gates in minimum number of EPR pairs, but also just optimizing circuits such that their connectivity is more appropriate for distribution. There's also the question of, doing efficient entanglement routing. So when we partition things and we send them over these primitives, we kind of assume that they will have EPR pairs, these entangled pairs. This is kind of the symbol that you can see in these graphs for them. And these things kind of need to be created on demand. And there is like this very big field, or this very important question of, well, how do we, generate these on demand and send them to the right places in a way that's reasonable for the speed of a network? And this, finally, kind of another one of the open questions, obviously this is not an exhaustive list, is the question of security. How do we do all of this securely and consider this concept that there could be malicious players in our setting?